Welcome to part 7 of video series on relational databases Informal Introduction. In this part, we will be talking about indexing. We already know that one of the primary purposes of any database is the ability to run queries. Databases are actually designed to run queries. And this is why query performance is very important. It means that query should run fast enough. Ideally, query should return results immediately, or at least it should return them as soon as possible. So far in this video series, all our queries returned their results immediately. But that was mainly because we were executing queries against very small tables, something like 20-25 rows. These tables are considered tiny for databases. Because for database, really important, significant table is something like 100 million records. And even this table is not actually the biggest the database can handle, but at least if you work with millions of records, you may start actually notice performance problem. Now, consider running the following SQL statement in some table. We will call it sale item, which keeps some items for sale. And every item has some number. We will call it item number. And suppose this table is pretty big. So suppose it has something like 100 million records or more. And let's try to execute this statement, select from sale item, where item number equal to a certain particular number. How the statement would run. Obviously, if you don't have any special tool which will help us, it will need to browse 100 million records, so all records in the table. Even if it finds records with item number quickly, for example, we are lucky enough and this record is at the very beginning, even then we still need to run it against the entire table because we don't know whether it's the only item with this number. In this form, as presented on the screen, this statement may return many records, not necessarily one. So unless we reach the very end of the table, we don't actually know whether we returned everything or not. So this statement will always scan entire table. And this is obviously very bad. And on the next slide, I will show you how slow this statement could be. But don't be upset yet, because fortunately, we have a tool to handle this, and this tool is called index. If we use index on this table, in this case, we will be browsing all records in the table. We will go to our target record immediately. So in order to run all these experiments with bigger table, I am creating this table first. You can see create table script on the top. I currently highlighted it. Then once this table has been created, I'm inserting at first 3 records into this table. We will not be using this name, category, subcategory columns. However, I still want to put some content into these columns because I really want to bring some big amount of data into tables. The more table we have, the more data we have in table, the more we will be able to see some performance problems and challenges. And now, in order to make this table really huge, I'm using some kind of trick. You can actually look at this highlighted statement now. This is insert statement, which inserts records into sale item table from itself. It's taking data from sale item table and it inserts them back into sale item table. So what the statement does, it actually duplicates records. It's taking existing records and inserting them again. And this statement is quite possible in SQL. It's not going to create any endless loop because at first it takes data and then it inserts data. So in the process of inserting, it's not taking any new records. So the statement works perfectly fine. And every time it's executed, the table size doubles. So at first we have 3 records, then we will have 6, then we will have 12, 24, etc. And in order to really make this very big table, I put this statement inside the loop while, and I run this loop 25 times. Once executed, this is going to create something like 100 million plus table. 100 million plus rows table. I have already executed all this cycle and table already has data. I am not going to execute it within this video because it's really taking pretty long time. Depending on the hardware you are using, it's maybe taking something like 10 minutes, maybe even more. Or it could be taking less if you have very powerful computer. However, it's very interesting point that for any performance testing, any performance experiment, you would really like to use some kind of underpowered computer, because if you use very powerful server with some ultra-fast processor, with some ultra-fast hard drive, you may not spot performance problems. And they will show up anyway, even if you use the same powerful server in production, because you may not see it on your particular machine. However, when you deploy your system into production and something like 1,000 clients are accessing your database simultaneously, the performance problem will show up even on very strong hardware. So far, I'm using some underpowered computer for this test, and I'm using it deliberately. And finally, the query we actually wanted to run. Select from sale item where we're looking for particular item number. So I have this query ready and I click execute button. And as you can see, nothing has been returned. And now if you look at the bottom right corner, here the one I'm currently pointing with cursor, you see that it's showing time it's running and time is increasing. So at this time it's already 15 seconds, 16 seconds, and it's still running. If you remember, it's very different from all queries you have seen before, because previously whenever I click at this execute button, you almost always see results immediately. Now you already see results. It returned one row. Now let's have a look again at the time, and you can see that it took 29 seconds, so almost half minute. This simple query was executed. And so far it's just very, very simple query. If we were joining big tables together, the situation will be much worse. So hope I convinced you that we really need indexes. We really need to have some tool, because scanning table when table is big enough is really could turn into some kind of performance disaster. So in order to solve this problem and avoid scanning entire table with 100 million records, we need a structure called index. What is index? Index model, the simple index model, is currently presented on the screen. So it is a structure which looks like some kind of binary tree. It means that at each level, it will be asking you some question, and depending on your answer, it will go to the next level on the left or on the right. For example, if you have data ranged between 1 and 100, then at first it will ask whether your value is less than 50 or more than 50. So it divided this span of values by half. Then, depending on your answer, it will ask whether it's less than 25 or whether it's less than 75. Then it will go to the next level. And finally, it will arrive at some bottom level, which will be pointing to your record. It could be pointing by keeping physical address, but more often it's keeping some kind of logical address of this record. The implementation of this could be very different in different database products, but the idea could be illustrated in this picture. And the idea is that you always need to run only a few steps to arrive at your destination. For example, for this binary tree, in order to find your record, you need to run at maximum logarithm based 2 of n steps, where n is number of your records. And I said maximum this number of steps because sometimes you could be lucky, you could actually find your number earlier. For example, if your value is 50, exactly, not less, not more, than at very first unit, you will probably already have some reference to your record. Also, I wanted to mention that even though it's called binary tree, and binary means normally it has two values, it's asking a question and going either to the left or the right, so it's only making two choices. But normally most product will have more values at the same level. So, for example, they could keep 10 values, range of 10 values on the same level. In this case, your first level will not be asking question whether it's less than 50 or more than 50, but it will be checking against 10 different ranges. Is it between 1 and 10? Is it between 10 and 20? Is it between 20 and 30? And so on. So you will actually make your decision earlier. And if you have 10 values on the same level, then the number of steps you need to perform will be logarithm based 10 of n. And this is really very low number even for very big n. For example, if n is 1 million, then this logarithm will be equal to 6, which means that in order to search within a table of million records, you only need 6 steps. So you only need to make 6 operations. So it's pretty fast. It also was mentioning that tree-like index is not the only index which is used in databases. There are other types of indexes. For example, there is hash index as well. There is even more interesting index which is called spatial index, and this index is used to handle geography data like latitude, longitude, or geometry data like geometry coordinates. We will not be actually studying these indexes in this video, but it was mentioned that they exist. The one which is presented on the screen, the tree-like index, is still the most common. This is probably the one which is used more often than others. And another important note, it's not only relational database who has indexes. All other database models like document, graph, model, other models, they normally also have indexes. So using or having database without indexes is even difficult to imagine. Databases are very much, I would say, dependent on indexes. Almost all querying, all processing of data is always involving some kind of indexing. So now let's go ahead and create some index in order to help our query to run much faster. We can create index within this statement, create index. After create index, we put some index name. We need to assign name for every index. And then we put table name. And in parentheses, we put column name we created index on. Or it could be actually set of columns. Index could be created on more than one column as well. So I already went ahead and executed this statement. It is obviously taking a while to execute because if you remember, we now have pretty big table. We now have 100 million records. And if you look at the right bottom corner of our window, this is where I am currently pointing this cursor, you can see that time to create this index was something like 3 minutes. So once index is available, we can now try to execute our original query again, and you will see the difference. So I have this query ready, and I click execute button. And now you see that result is coming immediately. You already saw immediate result before, but it was this table with about 20 records. And now you can see almost the same speed with table of 100 million records. And once again, look at this right bottom corner, which shows time what took to execute this query. It shows 000. It means the time was actually virtually undetectable. So obviously it took some time, but it was so small time, so our SQL server was not even able to catch it and show it to us. So you can now see what difference the index can make. So we just have seen that creating index was pretty simple and straightforward task, and it did give some positive results very quickly. Well, unfortunately, it's pretty simple and straightforward only in this very simple and basic example. But in general, indexing is one of pretty complex topics in databases, and it does require actually knowing a lot to use indexes effectively. Let's review some problems which we can see with indexes. So first of all, indexes speed up significantly all reading queries, means queries which start from select keyword or similar queries. And this is something you just witnessed. You saw how we sped up our select query perfectly. At the same time, they are known to cause problems for updating queries. Queries which inserting records, deleting records, updating records. These queries will be executed slower if you have many indexes on table. And this is because your system should maintain index. When you're doing, for example, delete or insert, it needs to rebuild at least part of the index. It needs to reflect it. When you update something, it may also need to restructure index, because index is storing all data, as you probably can guess, in sorted order. We just saw that index is binary tree. It needs to have data ordered. So if you change the value, this value may need to go to a different place. So in this case, there could be need to do some update to index. However, the way how it does slow down update queries is not comparable with the benefit how would it speed it up. What I mean that it could be speeding up your query something like 1,000 times, maybe million times sometimes. We just saw example, query without index was running 29 seconds and query with index was running for undetectable time, so we could not even see any fraction of second. The slowdown will not be that significant, so it will never slow down 1,000 times. It will probably slow down it to some percent if you're doing updates. But you always need to see how important it is for you. Sometimes these update queries may be even more important. For example, if you're running some real-time system and it needs to acquire data very quickly. Another problem, indexes are taking a lot of space. Indexes actually having as many records as your table itself, although they store less columns, but they do store all records. So it's actually taking space which is comparable to the size of initial table. Or if you have many indexes, their combined space may be even bigger than original tables. You may actually have double space of your table or triple space or more. So that could be concern, but not always concern, because this time storage is very cheap and we have very powerful hard drive which do not cost a lot and they have very big capacity, so it's not necessarily a big concern. However, something to think about. And finally, very unfortunately, but indexes do not always help. They help for certain pattern of queries. Let's review where index is helpful and where index is not very helpful. For example, the following three queries will definitely benefit from index. The first query is the one which we already know. This is the one which we already executed, and what is specific for this query is comparing a certain column to a particular value, and this column is indexes. So this query is a very good candidate to benefit from index. Another query which will also benefit from this binary tree index is so-called range query. This query, and now you see a little bit new syntax, it's using keyword between, and you can guess that it's finding all records where item number is between 1000 and 1020. So this is range query, which is looking for records in certain range, and index will be very useful for this query as well. And another query which will benefit from index is the query which is ordering by this column. As index has all data ordered, already pre-ordered, that in this case we can get this records directly from index in that order. Also pay attention to another new SQL syntax. We didn't use it before. It's saying top 10. Means that it's not taking actually all records which are returned by this query, but only first 10 records. And another important fact I wanted you to pay attention to, all these three queries actually have something in common. And what they have in common, they all return very few records. The first query is only returning one record, we already saw it. The second query will return something like 21 records, maybe more if there are some duplicates in item number. And the last query at maximum will return only 10 records and never more. And this is very important because index is very effective when you only return few records. Let's think that you actually increased this range and started to take, for example, the very first statement, item number equal to something. Let's say that we do not have the same data pattern as we currently have, and we have so many records with the same item number. In this case, index may be not very useful because if it's retrieving significant portion of the table, maybe 50% of table or 70% of entire table, your database product may decide that it doesn't need to use this index because it sees no benefits of this, and instead it can actually resort to scanning entire table, and this is essentially the same as it would be without index. So it's always a question actually whether index is useful or not. Let's see some examples where index very unlikely will be useful, or at least it will not be used effectively, or maybe not used at all. So the first example is very interesting because the statement which you currently see is exactly the same as previous first statement. So it's also retrieving the same record. As you see, I added 5 to item number, and I also added 5 to the right portion of the query. So it's essentially returning the same record. However, situation is very different. And this is because instead of saying simple comparison where item number equal to something, it means that some column equal to something. This is actually where index is always used. Well, not always, but maybe in most cases. Now I'm comparing expression. So item number plus 5 is certain expression. And many database products will not understand how to use it, and they will simply be scanning entire table because they do not see actually direct comparison of column to certain value. So very slight change to the statement actually made index not to be used at all, or at least not used effectively. And another example, I already mentioned before that previous statements were only retrieving few records. And now I actually executing the same statement as previous second statement, except that I extended range. It's not between 1000 and 1020, but now it's between 1 and 100 million, which means that it will return almost the same, almost entire table. Once again, your database product may decide that index is not necessary for this statement because it's returning entire table, so it would be better just to scan entire table, so the presence of index may not necessarily help in this case. Well, now you see that situation with indexes is more complex than it appeared before, and the main conclusion is indexing strategy requires a lot of knowledge and proper skills. And not only theoretical knowledge, it also requires a lot of experience because all these indexing strategies, they could be specific for particular product. So one product may use one strategy for executing query, another product may use a different strategy, and they could even differ between different versions of the same product. So within, for example, version 5, it's not understanding that item number plus 5 is the same as just previous statement, and version 6 of the same product may be more advanced, so it may actually do this transformation automatically and still apply index. And now let's check everything we were talking about so far in practice. The first query, you already know it pretty well. It works very fast. We are not even going to run it again. The second query I'm highlighting is our range query, and I click execute and run it, and you see that it runs immediately. And once again, pay attention to this execution time at the bottom right corner, and it is still undetectable. It's showing 0, so it runs perfectly fine. Our last query, the query which is accessing our table in certain order, so it's ordering by item number, is also going to run very fast. I click execute, I see results immediately, and again time is undetectable. And you can see, I will scroll it, that we actually start from item number 1, so we will start from very beginning, so it's all ordered properly. Now I can actually put this desk keyword here, which means that I want to order it in descending order rather than in ascending, and execute the statement again. And again, it runs very fast. Again, time is undetectable, it's 0, but this time, as you can see, we have big item numbers, so we actually approach a table from the opposite end. We now scanning very end of the table, and it's working perfectly fast, and this is all because of index. You can imagine what would happen if index did not exist. In this case, what will happen with this statement? It will almost run forever. And this is because it will not only scan sale item, but it will also need to order it in certain order. And ordering a huge table is taking really very big time. And now let's check what happens with our first well-known item if we just a little bit modify it. We already saw this on previous screen. I am adding 5 to item number, and I am also adding 5 to the value I compare with, which is essentially, as you understand, the same statement, the same logical statement as it was before. But now we modified our syntax. It means that index may not be used in this case. So we select this statement, I am clicking on execute, and now you see what's going on. It's now running and running and running, and time is increasing. So it's not lightning fast as it was before, and the only thing what happened is we added 5 here. So statement have finished. We now see a result which is expected. It's the same result as before. One interesting point, what I wanted to point you to is the time which is currently shown here, and now we see 10 seconds. Why it is interesting? Because if you remember our previous execution without index, it was 29 seconds, and now it's 10 seconds, so it's almost 3 times faster. It's not lightning fast, like it would be if your index was used properly, but it's still faster than executing it without index. And the reason for this is that instead of accessing entire table, our product SQL Server Express in this case is now able to get information from index. And index is actually smaller than table because index only stores a value for one column. So it did scan index quicker rather than it would scan table. So index is sometimes helping even if it's not really pointing you to the record, although this kind of use of index is not really very effective. And finally, I wanted to mention for you that all this information about how certain query was executed could be taken from so-called execution plan. And if you go to query menu, you can see actually that you can request display estimated execution plan, or you can see actual execution plan, which will be shown after query has been executed. So these execution plans are giving you very good explanation what query was doing, how index was used, or how index was not used. I'm not going to talk about execution plans within this video because execution plan is pretty advanced topic. It requires a lot of explanation, so I just don't want even to open this topic. But I do encourage you to check execution plans if you are going to use this product. Or if you are going to use different product, it may also provide some kind of execution plan explanation. Not all products provide this. Some cheaper or open source product may not have this facility available, but good relational database product always will provide some explanation to execution plan it has chosen when executing your query. It may be in graphical form, like it is available in SQL Server Express. It could be in some kind of text form. Sometimes some XML file could be produced. So it could come in different form, but it is very important to pick up a product which can show execution plan, because without this, you will be clueless of why some query is running slow, so what is going on. With execution plan, you can look inside and check and understand it. However, obviously, usage of execution plan requires even more skills and knowledge than just knowing about indexes. This is end of part 7 of video series on relational databases, informal introduction. In this part, we learned very important topic for all databases and relational databases in particular, and this topic was indexing. We saw that indexing could increase some queries enormously. We also saw that indexing is not very straightforward and there are some problems associated with this, and finally came to conclusion that proper indexing requires a lot of skills, knowledge, and experience.